Hi. So we are currently talking about compressible flows. Since we've been talking about incompressible flows for so long, I keep saying incompressible, but really we've transitioned to start talking about compressible flows. Right? Where the condition of incompressibility, we know it, the generally accepted condition of incompressibility, where the divergence of the velocity was taken to be equal to 0, that's no longer true. Okay, so this can be taken as one thing about compressible flows. The other thing about compressible flows is that the speed of sound waves, rather, sound waves are an essential feature of compressible flows. Right. So these are the two important things we have sort of highlighted so far. We have done a short derivation on the speed of sound, on trying to show how small disturbances in pressure and density travel at exactly one speed, okay, and that is the speed of sound, right? And what we did there, just by way of a very short recap, is you recall what we really did was we started with the mass and momentum continuity equation. We started first with the mass continuity equation. Written in Eulerian form for convenience. And then we also wrote the Euler equation, which is a momentum continuity equation, again written in the Euler equation. Also written in the Eulerian form, in other words, from the point of view of an observer who's standing in the lab. And so that would be this. Right, is equal to minus gradient of pressure. So we took these two equations. These are the two main equations we took. And then we said that the basic quantities, you see here, you look here, there are three variables, right? There's rho, there's u, and there's p. Eventually, there are three variables and only two equations. So eventually, we'll want to eliminate one of these variables. As it happens, we choose to eliminate p in favor of rho through what's called the sound speed. But the way the sound speed comes about, we'll have to, let's do a very quick recap. We've already done this when we met last, but it's useful to do a very quick recap, right? So, but you see, the point is, this is total density, total velocity, total pressure, right? But what those total density and total velocity are something like this. So the total density would be the sum of a background density plus a perturbation density. This is a background density, and this is a perturbation. Right? And what's the property of the background? The main thing about the background density is it is uniform in space and it's time invariant. It's not varying with time. In other words, d rho naught dt equals 0, and it's uniform in space. In other words, d rho naught dx equal to 0. And by dx I mean dy, d rho naught dy, d rho naught dz, everything. All of those are equal to 0, right? Not so for the perturbation, of course. So you start out with a uniform background, and the same thing, we have the same philosophy for the velocity as well. For that matter, we have the same philosophy for the pressure. So the total pressure is the sum of a background pressure plus a perturbed pressure, and the background pressure is time invariant. d over dt of p naught is 0, and it's also uniform in space, so that any spatial derivative of p naught is 0. Not so for the perturbed pressure. And the same thing for the velocity. The velocity is u naught plus u1. Except now, without loss of generality, we just take this to be equal to 0. There's no background velocity. In other words, there's no breeze through the room. Okay. So what we do is we substitute this u equals u naught plus u1, p equals p naught plus p1, and rho equals rho naught plus rho 1 into these two equations. Okay. And there's one more important thing to note, is that all the perturbed quantities all perturbations are small, i.e. Rho 1 over rho naught, p1 over p naught, everything is much, much less than 1. Okay, so this is the other central assumption that we make. So any perturbation, the density perturbation that I launch or the pressure perturbation that I launch by virtue of speaking, these are small perturbations. These are the density perturbations rho 1. It's small in comparison with the background, the magnitude thereof. Okay, so this is another central assumption. And as a consequence of this assumption, as a consequence of the smallness of the perturbations, and I write this in quotes. Okay, what happens is you can neglect products of small quantities, neglect products of small quantities. What do I mean by this? For instance, I'm allowed to neglect things like say for instance, when you substitute things like rho equals rho naught plus rho 1 in the mass continuity equation. So you see, you would have rho naught plus rho 1 here and u naught plus u1 here, but u naught is of course 0. So the mass continuity, I'll just give you an example, becomes d over dt rho naught plus rho 1, right, plus rho naught plus, there used to be just a rho here, and that's rho naught plus rho 1, and there used to be just a rho here, and that's now rho naught plus rho 1 times there used to be a u here, and that's u naught plus u1, but we know that u naught is 0, therefore you just have the u1 here. Now what you do is, first of all, we say as a consequence of the uniformity of rho 1, d rho naught dt equals 0, of course, whereas we're not saying anything about d rho 1 over dt, we retain that as it is. And this quantity rho 1 is neglected. Okay, because this involves in some sense the product of two small quantities. Okay, so that's what I mean by this, neglect products of small quantities. This is what I mean by that. This is an example of what I mean by that. Okay? And so this process of neglecting products of small quantities is called the process of linearization. I mean, in principle, if you were to able to relate U1 to rho 1, this would become like a nonlinear combination, right? But we neglect that. So you only have a linear combination, rho naught and U1. Rho naught is a background quantity, so this is linear in U1, right? So this is essentially the process of linearization, and as a consequence, what we have is the linearized version of the mass and momentum conservation equations. That's one thing, and the linearized and linearized momentum conservation equation becomes rho naught so this would be equation 3 and equation 4. Okay, now using this is where we introduce the sound speed using using the chain rule. This is just simply the chain rule for differentiation, right? That's all this is. And we identify this as we simply, for the time being, we just say this is Cs squared. Later on, we'll discover that this is really the square of the speed of wave propagation. Using this and combining 3 and 4. What are 3 and 4? 3 and 4 are this and this. Okay, so combining 3 and 4, we get a wave equation you're combining two first order differential equations, you are bound to get a second order equation. And same thing for U1. Like this, and these are essentially wave equations. And what's the speed of propagation of the wave? And the wave speed equals C sub s. So C sub s is the characteristic speed, and I say characteristic because just to emphasize that it's the one and only speed at which small, and I emphasize small in the sense that rho 1 over rho naught is much less than 1, P1 over P naught is much less than 1, so on and so forth. Density and pressure perturbations propagate. So this was a very quick recap of how the speed of sound arises naturally from just the mass and momentum continuity equations, right? So we did this, and then we did a little bit of Fourier analysis, and where we essentially said we Fourier analyzed where we said all quantities go as exponential I k x minus I omega t. And as a consequence, any kind of d over dt becomes a minus I omega, right? And any kind of d over dx becomes a I k, right? That's how it goes. And using this in these two wave equations, we get the dispersion relation, which is always a dispersion relation, is always a, i.e. a relation between omega and k. The omega here, the temporal frequency and the spatial frequency. That's what the dispersion relation is. And for sound waves, it is simply given by omega square equals cs square times k square, i.e. sound waves are non-dispersive. It's not like the phenomenon of light waves propagating through a prism, where the phase velocity, the group velocity for that matter, of light, of different wavelengths of light, in other words, the different temporal frequency of light is different inside a prism. And that's why monochromatic light splits up into its components. That's not the case with sound waves. Okay, different frequencies of sound waves propagate at the same speed. Whether I'm speaking at a high frequency or a low frequency, the speed of propagation is always the same, and that's the speed of sound. So just to once again recap, because this is a very important thing, this is a direct consequence of compressibility. Sound waves are a consequence of compressibility. In a given medium characterized by a given background density, pressure and temperature, it represents the characteristic speed at which small disturbances in what? Disturbances in density and pressure, these small disturbances propagate. It's a characteristic speed. Okay, and we wrote down that we did this, right? We said cs squared equals, this was the basic definition, you remember, of the speed of sound, like this. So if there's the case, then for a polytropic medium, in other words, for a polytropic relation, which goes where you have p proportional to rho raised to some n, right? If you plug this in here, you get cs squared equals n p over rho, right? And generally n, as you know, n equals 1 is isothermal, and n equals 5/3 adiabatic, right? So these are two commonly invoked limits of the polytropic relation. So you would have two different kinds of speed of sound. Yeah, so normally what happens is, you're often asked, okay, so you're talking about the speed of sound, you're talking about the characteristic speed at which small density perturbations propagate, but what is the thermodynamics of these density perturbations? How do these small, compressions and rarefactions, what's the thermodynamics? Is it an isothermal compression and rarefaction, or is it an adiabatic compression and rarefaction? If you can answer that question, you'll have the accurate definition of speed of sound. So you can have two different kinds of speeds of sound, right? Depending upon, you can have an isothermal speed of sound, you can have an adiabatic speed of sound, you can have something in between as well, depending upon the value of n. As we remarked a little earlier, the value of n, this is really kind of a cheap energy equation. This value of n embodies all the energy dissipation and processes that can be happening. So the actual speed of sound, although formally is defined like this, the actual value will depend upon the thermodynamics of the compressions and rarefactions, and the two limits are an isothermal process and an adiabatic process. Depending upon the value of n, the speed of sound can vary. Okay, and couple of other things. You see, the speed of sound is linked to pressure disturbances, right? So it is linked to communication. I am able to communicate with you via the speed of sound, right? So communication or propagation in medium happens at one characteristic speed, the speed of sound. In a philosophical way, it's similar to the speed of light. Okay, so the speed of light is of course invariant, whereas the speed of sound can be quite varying, as we saw. But that apart, you can see that the speed of sound can be linked to the principle of causality. So as in you cannot hear me before sound waves have a chance to propagate from me to you. Hence the link to the principle of causality, right? And unlike the speed of light, objects and flow speeds, for instance, can indeed exceed the speed of sound. That's not so with the speed of light, of course. But the dynamics in the two cases, whether the object or the flow speed is traveling subsonically or supersonically, in these two situations, the dynamics of the flow will be very, very different. In other words, subsonic flows and supersonic flows are very different in nature. And when we meet next, we will talk about the details of these. Thank you.